Ladies and gentlemen, a very good afternoon. My name is Desmond Ang, your Master of Ceremony for today. First of all, on behalf of the organizer, I would like to thank you for your attendance in this inaugural lecture, which will be delivered by Professor Dr. Christoper Jesudason from the Department of Chemistry, Fakulti of Sains, Universiti Malaya. The inaugural lecture will commence shortly. To ensure the event runs smoothly, I would like to highlight a few house rules before we begin. I would appreciate very much if all guests could rise when I announce the arrival of Professor Dr. Zanaria Abdullah, the Dean of Science, University Malaya, who will be chairing this lecture, and the arrival of Professor Dr. Christoper Jesudason. Kindly remain standing for the national anthems and the UM song upon their arrivals. And as a support for Professor Dr. Christoper Jesudason, I would appreciate it very much if he could remain in this hall till the end of the event. I would also like to remind everyone to switch off your mobile phones, or please set your phones to the silent mode to avoid any interference during the lecture. And if the alarm bell rang, everyone are required to move in a calm state to the emergency assembly point using the door on the right or on my left. You will be assisted by staff on duty. Sekiranya loceng penggara berbunyi, tuan-puan dikendaki bergerak dalam keadaan tenang menggunakan pintu yang berada di kanan atau di kiri saya untuk bergerak menuju ke tempat berkumpul kecemasan. Tuan-puan akan dibantu oleh petugas. Your cooperation is very much appreciated. Thank you. announcing the arrival of Professor Dr. Zanaria Abdullah, the Dean of Science, University of Malaya, who will chair this afternoon's inaugural lecture, and Professor Dr. Christoper Jesudason. Ladies and gentlemen, kindly remain standing for national anthems and University Malaya song.
Universiti Malaya, kebanggaan kita semua, bertambah para ilmuwan di berbagai lapangan. Kami bertekad di hati mencapai cita murni, tradisi kecemerlangan menepati wawasan. Di sini kami sedang berbakti, terus berinovasi. Kami harapan generasi muda, teras nusa dan bangsa. Varsity kesayanganku, sungguh banyak jasamu membentuk insan mulia, berilmu berbudaya. Di sini kami sedang berbakti, terus berinovasi. Kami harapan generasi muda, teras nusa dan bangsa. Varsity kesayanganku, sungguh banyak jasamu membentuk insan mulia, berilmu berbudaya.
Ladies and gentlemen, please be seated. A very good afternoon, Professor Dr. Zanaria Abdullah, the Dean of Science, University of Malaya, Professor Dr. Christoper Jesudason, distinguished guests, the management of Faculty of Science, ladies and gentlemen. Welcome to the inaugural lecture by Professor Dr. Christoper Jesudason, entitled Some Consequences of Posing Almost Impossible Questions in Physical Sciences. Without further delay, ladies and gentlemen, with great pleasure, I would like to invite Professor Dr. Zanaria Abdullah to chair the lecture and to introduce Professor Dr. Christoper Jesudason.
Thank you, Desmond. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon. Christoper G. Jesudason. Christoper G. Jesudason received an scholarship to complete his sixth form at Preston School, England in 1975. He won a place at the Queen's College, Cambridge to study natural sciences, graduating in 1980 with a BA degree specializing in theoretical chemistry and applied mathematics. He conducted post-BA research here in UN under Professor in spin-free quantum chemistry from 1980 to 1982. He was awarded an MA degree from Cambridge University in 1984. Emeritus Professor Darwin W. Smith, a known quantum chemist, was his major professor for his PhD dissertation entitled Studies in Thermodynamics from University of Georgia, USA, awarded in 1986, where he had a free hand in research. After UGA, Christoper spent 2 years in Montana State University as a postdoctoral fellow. He then joined University of Malaya on the 1st of July, 1989. During his years in University of Malaya, i.e. from 1989 to now, his unconventional outcomes in their research, including deriving the black body spectrum classically with the Planck constant given a precise meaning in terms of measurable variables, and the consequence of his theory for the thermal radioactive heat transfer and the Kirchhoff radiation laws. Other results included theorems in electrochemistry and the invalidity of time reversibility that underpins the central tenets in science. In statistical mechanics, he postulated in 1989 that the recoverable transition between a zero entropy trajectory that was recently validated in heat conduction. Several other unconventional results were analytically proven in quantum and statistical mechanics. He spent his first sabbatical, that is in 1994 to 1995, at the National Chemistry Institute, Slovenia, where he worked on the computational statistical mechanics. He was then promoted to associate professor in November 2000. Then he took his second sabbatical leave in 2001, and he spent his time at the Institute for Physical Chemistry, Trondheim, to study the computational NEMD, or non-equilibrium thermodynamics, using non-synthetic methods required in his NEMD work. And he devoted his sabbatical research leave in 2007 to work on charge system simulation in Finland and the Arenas laboratory in Stockholm. He was then promoted to professor in December 31st, 2008. And his fourth sabbatical research leave was at Queen University, Belfast, in 2013 at the Atomistic Simulation Center, working on molecular dynamics of ionized liquids in molecular organic frameworks. And his last sabbatical was spent at the University of Calgary, where he began molecular dynamic studies of deep enteric solvents. With the prospects of retirement looming, he hopes to spend some of his free time available in the years ahead to build up the postgraduate research capacity at the regional level among interested parties in Asian and many research centers he has visited during his tenure here as an academic. Without further ado, I would like to invite Prof. Jesudason to deliver his inaugural lecture.
Thank you very much for your kind introduction. Ladies and gentlemen, this is an inaugural lecture suggestive of a presentation given by someone at the threshold of a promising career with an expiry date and institutional support far into the very distant future. None of these things apply to me in the immediate sense. I'm due for retirement in the not-too-distant future and will not be recounting or inaugurating future research projects based on what has been achieved to date in this lecture. What I can inaugurate, however, is a style of doing research and describe what the consequences of this style were in my case. One objective of this lecture is not to present a summary of results achieved over the last 28 years as disconnected facts. No, rather what is being recounted within the facts is a method or style of doing science within the milieu that one finds oneself in, sometimes impoverished in one sense or another. This method is a response to both the immediate environment, and the results of those responses constitutes the basis for further and future investigation. This method cannot deplete the scientific milieu of its value and its social, physical, and knowledge infrastructure. Since science has become an internationally acknowledged universal paradigm, it functions as a major means of control and regulation in peaceful times with its own pecking order. Official work here in and in fact elsewhere, implies that for academic advancement and accreditation, one must seek and secure niche areas of international research that would lead to publishable results in journals with high impact metrics and citations, which would necessitate very elaborate networking strategies, in addition to thematic selections that are consonant with the prevailing demands to achieve high and immediate visibility. The work presented here did not follow that route, even if some or much of the work was a response and critique of work in high visibility journals in modern times. Then there was the need to examine the foundations of the sciences that goes back decades and centuries, that is not part of the normal methods of research in the international bureaucracy. In all cases, however, the main driving force for the research reported here was curiosity-driven, based on the need to question and clarify the underlying assumptions of dominant paradigms, and to add to their influence if they appeared beautiful, coherent, and had a breadth that referred to all peoples. This elaboration became the basis of other work, where cause leads to effect, which becomes the cause again, leading to a self-determining spiral of activity not strongly influenced by the international scientific marketplace. A university can only benefit from such activity if the property of anamnesis or memory retention and deployment is in place, so that the collective experiences of generations of academics and skilled supporting technicians and staff are retained in the prevailing social and physical infrastructure and built up and extended by the next generation of workers. If such anamnesis facilities are absent, then one is dealing with a situation of significant hemorrhaging, where each generation begins at square one, unable to utilize and add on to the intellectual, social, and physical capital of the preceding generation. The wealth, power, and capacity of all major academic institutions are ultimately based on this process made possible by cultural anamnesis that enables such bodies to be self-determining in terms of the work and research that they perform and the effectiveness and economy in which they are able to solve problems that arise from their environments. Hopefully, this lecture will in some measure impress upon the hearer the possibility that responses to the milieu can indeed open up a future that one can work towards, providing goals, motivation, and capacity to solve problems that our society confronts in a relevant and affordable manner. Therefore, I sometimes wonder whether, in some cases, the funding crisis that we face is in part due to the fact that we have not done science having the aforementioned features and characteristics that are present in all successful and capable institutions with their intact anamnesis. With the end of this preamble, let me now breeze through the technical aspects of this lecture, which I hope will illustrate some of the points made thus far. Thank you. Right. Right, so what we shall do now is I will have to turn my head a bit and look into the screen and begin to give the lecture. As we can see, is this working? Oh, is this working? It's not working. No, it's dead. Anyway. The title of this lecture will be Some Consequences of Posing Almost Impossible Questions in the Physical Sciences. Now, we will move on. It doesn't matter. It's not working. Okay, now, this is an outline of the description of the work that we are going to look at. There are altogether 8 topics, exceedingly broad. And I think that this broad base is only possible if somebody is working at the fringes of a global system which, by its very nature, restricts one's focus for management reasons, creating niche areas that academics find themselves in. No such niche areas seem to be indicated here. So we will go on to the introductory statements. A portion of the following research areas include the following topics. Sorry. That's funny indeed. Okay, let's look into the first topic, which is thermodynamics. Before we go on to the lecture, I just want to allow your mind to capture 3 images. One is that of a cylinder with a lot of molecules, and what happens if you apply a force to it? You know, you have work done, and what happens then to the situation inside? The second one is that if you have a system, imagine you have a system which is in non-equilibrium and which is in a steady state. Draw a line within the system and look into a small volume within it and trace a path round. That would constitute a closed loop, and in calculus it'll be a complete cycle about a closed loop. Third image is that if you have motion of a system in positive time, then in reverse time it's supposed to go through the same motion, and it's said to trace exactly the same path as a movie reverse. Such a property is said to give rise to new phenomena. So we shall look into this. Now, this image of the system with a loop inside was what we performed. This is actually the earliest work that I did. And this is based on an extension of the work that Benefic and Quay performed But what I did was to look into the system and its loop and looked into the heat transfers that could take place within a subsystem in a non-equilibrium system. In other words, I have a huge loop, and from there, I can trace a path. Now I can define various entropy production terms, and what happens is that I am able to make a deduction of this entropy term having this inequality, where this is the steady state entropy rate, and this is when it is relaxing to the state. A are the external variables, the forces that are applied to the system in order to maintain the fluxes. Now, this is not the sigma entropy of Prigogine. And in fact, this system, under a lot of assumptions, reduces to the Prigogine entropy, which is non-analytical and approximate in nature. So this is one example where Prigogine made a big noise when he was alive about his entropy production principle, but it's basically an extremely lame and weak system. He produces a lot of spaghetti, but not so rational. So this was done at a very early phase of my work. Now, looking into thermomagnetic effects, there were two things that were done. The one was to look into a normal Kelvin thermocouple that we all use. And I'm not going to talk about it here, but I found out that it was absolutely not, in fact, very accurate, and that the more accurate version, which was published in the Asian Journal of Physics, and also I think in a Romanian journal. The other thing that I did was to look into the continuous Kelvin thermocouple, and was able to deduce by the previous work on entropy that I described, non-equilibrium steady state, new expressions which are exceedingly important when it comes to the use of thermoelectric devices. Another very important deduction has got to do with heat engines. One of it has got to do with I pressed on the wrong button, on the Kelvin heat engine. The Kelvin heat engine is nothing more. Imagine you have a tube that loops on itself with a fluid. One side of the tube is subjected to one temperature, and the other side of the tube is subjected to another temperature. And what happens then is that you're going to find circulation within the medium. That circulation within the medium is a source of motive power. So that's the Kelvin engine. And from the Kelvin engine, the phenomenological equations of this engine, which is obviously important if you want to do mechanical work, is given, for example, by this expression here. Now, another very important thing, following the Benefi and Quay hypothesis, why do I mention these people? Because when they write, he's a Jesuit scientist, rigorous, but when people like him writes about science, he's speaking about, first of all, wonder in science, and wanting to say something that is relevant to the whole world. And there is such a spirit in the way that Paul Quay, who's now dead, and his student wrote these things, that it seems so attractive and beautiful to me. That's the reason why I then base whatever work that I do on these things. And he was not talking trivial things. He was looking into the Fourier principle, which is basically the foundation of the second law, that some second law statements say that if you have two temperature sources, the heat, conductive heat, will always flow from the hot to the colder source and not the other way. And from there you can derive all the laws of thermodynamics. So anyway, he came up with this, and what I did was to making use of the same ensemble method of taking a loop within a steady state, was able to derive the reciprocity relations to any order analytically. The Onsager relations, which won the Nobel Prize, right, had to make use of time reversal invariance or the principle of microscopic reversibility. The picture that I showed about the movie of things going forward and backwards, that was what? This cardinal principle was considered true by the biggest names. And I won't go into the politics of publication and so on. It's such a waste of time and doesn't make for pleasant hearing. But this work was published, and it was also presented at the AAA conference in San Diego, the AIP as well, where I rigorously show that this principle, which underlies the whole of quantum theory and mechanics and everything, and a lot of other dynamical equations to be mathematically false. There we are. So the point here, what am I trying to say? That in whatever circumstances that one finds oneself, if you are led by your mind, by the environment, and by your concern over the world, you will be able to say things. You don't need $1 billion budget or a CERN, account to do science. That's my point. Social solidarity and concern for yourselves determines so much of what excellent science is. All right, so now another peculiar thing, again, in an impoverished state, but this is also an important thing. And I also have to thank Dr. Lakshmi Kantam, professor, one of the most eminent mathematicians in America, having met him, and he was exceedingly sympathetic to my work, although he was a pure analyst. Now here, what I do was, if you look into the development of thermodynamics, which was developed by Carnot, he took one engine, which was a working substance. You have the working substance, you have the piston and a cylinder, for example, and then you subject it to different gradients. You have expansion, contraction, and then from there you get the Carnot cycle. Now this Carnot cycle is also used ultimately, the entropy term that you get from this Carnot cycle has been extended by conventional thermodynamics to multi-component systems, to open systems, including, even if it's an equilibrium system, open systems. You still make use of that same engine which has got only a working fluid within it, right? In other words, it's a closed system. The engine is closed, and yet we try to make deductions of open systems when you have to inject materials inside, and you also have to do work on the system. And the third thing is that you have to transfer heat into the open system. So it seemed rather strange to me that after 200 years or more, people were still talking about the Carnot system, which is closed, to describe open system thermodynamics. Now, unlike the other ones, where I postulate an entropy form, what I did here was, in a mathematical way, rigorously created an engine that was open. That is, it was diathermal. It was permeable to heat and also to material transfer. You had adiabatic, isothermal steps, and you also had material input carried out reversibly. Now, this is a huge work But some of the things that I found out from here is that you have two types of entropies coming out and two types of Clausius inequalities. It also clearly resolves a lot of contradictions in the Denbigh treatment of classical entropy. You know, Denbigh wrote a book, Classical Thermodynamics, and it's circular reasoning. So a lot of these things were resolved. The other thing is that BCU, again published in the highest impact journals in the world with the highest citations. There's a book in University of Malaya with his irreversible thermodynamics, and this I show to be analytically incorrect, completely false, but very highly cited, you know. So I wish you well in your international careers, you know. Okay, so there we are. You can check on the references. So we go on to statistical mechanics, thermodynamics with some electrochemical applications. Now again, I go back to the BQ theory, simply because I admired these people, the personalities of these people. Even if the work was mathematical, and for me, I looked into the nature of how they worked, and that was appealing. Now, what was funny here was that BQ in their definitions talked and used the term recoverable to speak about a process that could somehow recover some type of maximum work. I used it in a different sense, and this was when I was in Montana and people were interested in thermal desorption. If you have a flat plate and you have atoms on the plate, the atoms leave. So it seemed to me that imagine when the atoms are here at time 0 and suddenly they begin to dissolve because there's a potential there and you have the flat plate is maintained at a fixed temperature. So there's an interaction with the potential and the particles and it leaves. So the way I looked at it was to look upon a plane and you had an interaction and suddenly you had desorption. So it seemed to me that all the particles here, n in number, leave n in number, right? Very simple, childishly simple. So in other words, the number of particles were conserved, and if we say that all these things happen within a time, relaxation time tau, you have energy interaction and suddenly all the particles leaving. Okay, this is in one dimension. So thinking very hard about it, I decided that if the particle numbers are preserved, then it means that the phase space, this volume element multiplied by the density was preserved before the interaction that kicks the particle and after the particle leaves. Before and after the prime and the non-prime coordinates over here. So we can see the primed and non-prime. So this simple view led me to develop statistical mechanics where if this is the density, it means that along the trajectory, the entropy had to be conserved. And so this was the development of a zero entropy trajectory. And it seemed maybe, it was published 89, maybe 91. It's nearly nearly 30 years. And so some of these things, and I mentioned in that paper a non-Liouville type equation. This is the type of Liouville equation that you have in dynamics. And it seemed to me that you had, and I stated it very clearly, and I also developed a Jacobian. identity to describe this process. It's statistical. It is not in Liouville space. To those that are not so familiar, Liouville space is the momentum spatial coordinates of dynamical systems. Now we go to a little bit of cartoons for your imagination. There will be two of them. A black body cavity. You have a 3D buildup of cavity radiation, and if you put a pinhole, you will get radiation coming out. And the power is through the well-known Boltzmann-Stefan law, T to the 4. Also keep in mind that if you have a string of particles, like a necklace with an intermolecular potential, this is a 1D lattice, vibrating, and if you subject it to two different temperatures, you get heat flow. And also, if you are dealing with a zero entropy trajectory, somehow this delta S, which is Q1 of a series of particles before the interaction and after the interaction, when they leave at a different temperature, you get zero. And this is also the Carnot concept. Okay? Now, the other thing is that if you have a flat sheet, notice that over here, it's not a flat sheet, it's a 3D sheet, and you have T to the 4. All the engineers in the world, all the engineers and all the scientists have made use of the various supposed laws of thermodynamics to deduce, therefore, that if you have any emission, it has to be T to the 4 in the radiation. I will show later that that was not what I thought. And also, if you remember a few years ago, the Chandrayaan spacecraft, when it went around the moon, they were on a budget, these people, but it got heated up. They are very good at computations, the Indian people, but their spacecraft heated up. They were the first to discover water on the moon, despite the Americans going there with Apollo, apparently. But the Chandrayaan spacecraft overheated, and I just wondered whether they were making use of the standard T to the 4 engineering assumption. This is just a guess. I did write to them and even quoted the paper, which was an Indian paper, but they never replied. But I think that was at least my contribution to technology. Okay, so this is the thermal entropy based on this zero entropy trajectory. If there is no change in an entropy in a steady state system, you get this remarkable equation which makes sense. It's a type of a material, a divergence of the velocity of the stream flow is zero, which is a reasonable result which we all accept. The other thing, now this is really, really weird, it demonstrated that the Carnot theorem could be reduced to local form in this Indian Journal of Pure and Applied Physics, which stood in contradiction to the Benefi and Quay statements that believed that the laws of thermodynamics, when it came to work heat transformations, were always of a global nature. In other words, the Carnot cycle refers to a global, non-localized phenomena. Now, what we did in 1991 was to show, in fact, that the Carnot theorem seems to be observable, or it could be possible that, in fact, this optimization of work heat could be local in nature. And so I did so much computations, again alone, on my computer, and after so much flack and God knows what, I managed to demonstrate in this journal that in fact the heat, conductive heat, which is defined to be heat by thermodynamical definition, heat is that form of energy that traverses a boundary as a result of a temperature difference. And therefore, by implication, conductive heat must be thermal heat of the type that you study in your Carnot engine and in thermodynamics and in your chemistry, right? Q, the Q variable. Now, what is strange here is that I showed after 30 years from the first deduction that heat transfer in a thermal gradient is already an optimized process. Whereas when you teach chemistry or when everybody talks about chemistry, they talk about heat going in at one temperature, coming out at another temperature, and then you get a work done, right? You need to have a cycle. But here we are saying that heat itself is an optimized trajectory. Now, this is not just theoretically interesting, but I think that it means that it is possible to have methods of tapping work from just heat flow without anything else. This is the implication. And so this is a technological thing that many people have been, when you go to conferences regarding the second law and work, they say that the bottleneck basically has got to do with the fact that it all happens in a cycle, and it's not local, but it's global. So this then enables, I think, further technological investigation. And then there are many other things. You know, you have the Katauri statement about the inaccessibility of certain adiabatic states. I wonder whether if both adiabatic and now heat transfer are already optimized, then what can we say about the adiabatic states? Is there a more general theorem? Now that is for future. Okay, now at that time, when I prepared this lecture, it was in an earlier phase, and I'm preserving it for history to show that in this earlier slide, a disintegrating Carnot engine was an optimal device. And what happens is that on the heels of these things, you suddenly have this eminent man, Tuckerman and his whole band of God knows whom, coming up with these ideas where they were so convinced that they could use the Liouville equation to explain things that were almost identical in form to what I was saying. And so I show, in fact, that the Liouville equation, again, a very central equation in the whole of science, again to be largely erroneous. So these are top people with the highest impact factors and citations in the world, okay? So there we are. All right, curiosity, 1989, long time ago. Remember that photograph of a piston, a cylinder with a piston with a lot of molecules inside? Well, in this field of dynamics, Langevin theory as it is called, it has been understood that the velocity of the particles, because it's undergoing collisions, is non-analytical, and you do not really have a derivative of the velocity. And so everybody develops equations based on the flow of on the changes of the forces, and you take correlation functions of the forces, and there you get all your stuff. So I decided, let's be a bit bold and take some type of stochastic derivative and actually look into the velocity. In other words, do the opposite, okay? And I found that by doing that, you derive this simple theorem within a short enough period of time t. And this, you know, if you have a piston and you are doing work, it predicts this that the increment of work will be related to this. And if you look into your definition of the diffusion coefficient, you find that it's very similar to this. So in other words, diffusion in some way, an aspect of irreversibility, is completely related to work within the system. Obviously, more thinking will be done. Future generations who are caught up, maybe like somebody will go through a dusty bookshelf or maybe an old internet archive and pick this up, just like what Kelvin did with Carnot's paper. He got it from a dusty Parisian bookshop, you know, and he worked on it, and he came up with some beautiful ideas. Okay, a simplified Langevin theory. I will go fast because I did promise that I will breeze through, and I have my stopwatch here to make sure it's within 1 hour. Now, what I did, again, I have to thank Malaysia and also India, but I won't go into the politics, okay? I did a simple Langevin equation treatment of the black body radiator, again using completely unconventional methods, solving this differential equation, but saying that after an oscillation, it breaks up, okay? And you have different force constants. Very much like your transition state theory, you're supposed to have within one vibrational period and it disintegrates, right? So I made use of that, and I've never seen this peculiar concept used actually in all the mathematics that I've read with regard to simple first order coarse grained Brownian, treatment. So I used this, and when I did that, I could derive the Planck constant exactly in this way with all the terms pertaining to the system involved. Now, one of the funny things that I couldn't believe in, and I thought I was wrong, I just couldn't believe in. This is important. It means that you can actually compute that this Planck constant did not come from heaven, that it is basically, it is not a heavenly thing, but basically it is, in other words, compounded out of other things. And so here it's for the next generation of people to reduce the Planck constant to a series of other terms. You know what I'm saying? That it is not, it's not made in heaven. That's the message. So here, the thing that I couldn't understand is that when I developed these equations, I considered a box, and the surface of the lining of the cavity is a surface. In other words, it's two-dimensional. And what I couldn't understand was that under these assumptions, you had P, the power radiation, seems to be given by KT dash. In other words, it's first power, okay? Whereas every engineer on the planet always parametrizes their equation according to T to the 4. You look into all the engineering textbooks. And I had to read all of them, by the way, in the course of my work. Okay. I notice if you're asking fundamental questions, you have to work 18 to 20 hours a day because you are not part of the international bureaucracy. Things don't fall in your lap. You do this, we'll get you that. It doesn't work like that. And also, I want to impress another thing. What I thought about 30 years ago, I only understand it now. 30 years later, I'm able to show that heat conduction, for example, is a recoverable zero entropy trajectory with regard to the streamline of flow. Now, that was a very outlandish thing in 1989. It took 30 years. Now, if you have a KPI or a grant and they want everything done in 3 years, with a Gantt chart, how do you ever come to terms with that type of research, when you have to struggle in order to give coherence? Hamilton did the same. His children used to come, Daddy, Daddy, have you got this equation? No, 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 for 20 years until something happened. But something funny here, I couldn't understand this T to the 1. So anyway, what did I do? I will come back to that. I did do something as a theoretician, but let's go back to Liouville's theorem. This is a standard Hamiltonian. And by looking into the standard Hamiltonian, I found out that these things follow, and I won't go into details. And basically, you get childish equations that cannot in any way describe the motion of systems as people have done for the last God knows how many years, all right? Trivial. So I couldn't just leave it there. I had to give a reason why a lot of the methods that are used in statistical mechanics work. In particular, Gibbs hypothesized that the canonical density is given by this form. By the way, all the work in recurrence, the Poincaré and Zermelo recurrence theorems is based on the reality of the Liouville equation, including Birkhoff at Harvard, and all big names. These are the biggest names in the world. And the Liouville thing is only true in a trivial sense. All these things are absolutely questionable. Absolutely questionable. So what do we do? Okay, this is a big story, but not a big story, but in statistical mechanics, you have an ensemble space where a system is represented by one point. That's called gamma space, all right? Then you also have the particle with its individual trajectories, individual coordinates. So I've partitioned the two into the smaller ones representing the mu space, mu and gamma, it's a standard terminology, and P and Q are the ensemble coordinates, okay? And then another thing is that when you have ensembles put together, they interact. Now, normal statistical mechanics never looks into that, or they will question when they cannot explain something, they say it must be due to that. So I put all this together and just developed, and notice this F here is the non-Liouville density. And from there, and by making use of Hamilton's equation, I'm able to derive a stochastic probabilistic Liouville equation. That's the reason why it works in science, not because the analytical Liouville equation works, because we showed doesn't, it's ridiculous, but because of the statistical nature, you know. It works because of this. All right. Now, again, Tuckerman, when he was at my heels, you know, because everything has got to be centered in Rome, you know, in the Roman culture, so they need to have everything centered, and I've seen this so many times in my career, I'm not going to talk about these things. But they thought that they will explain what I was trying to say by using the Liouville theorem and, you know, even Jacobians. You don't have Jacobians in the Liouville theorem, but basically it just cannot hold what they said. So that's the reason why I think that Prof. Danare didn't have time to say some of the things in a biodata. What is very important is the preservation of the environment here in terms of protecting workers. They are so vulnerable. If you are dealing with an international order that sees itself as a pyramid with all things centered in one place, people in other parts of the world are in a terribly vulnerable position, you know, not just in terms of the themes of the research that takes away from what they should be doing, but also in terms of many other things. Now, I've only at slide 26 when they're 66, so I will breeze through. In electrochemistry, I want you to think of just electrodes and simple things like a constant, and here the CD is a derived equation, simple equation for the capacitance. In order to compute the capacitance, it would require very fine engineering capabilities, 24/7, moving electrodes, measuring them, and doing all kinds of things to get rid of all the other effects in order to calculate what the actual capacitance is. You know? So we really need to have exceedingly high quality technicians, and even I spoke to a young Malay lecturer, woman, and she says to do her ultrasonics, they make instruments there, and without being able to make it, she cannot do her research. So we need that. Okay, so electrode theorems. What I did was that I made use of the Hohenberg and Kern. At that time, earlier on in the 90s, they never had proper DFT functionals like what you use now routinely. And I used the Hohenberg and Kern expansion, for the electron gas, and showed that this was the form of the chemical potential rather than everything that is used in solid state, which is of this form. I noticed that, again, I've been not anticipated, but people have been at my heels, where this form is now being presented in unofficial documents, This work, by the way, was taken off. This is a ISI journal. Suddenly it was discontinued, and I published this work, and I've republished it as a review in International Journal of Molecular Sciences, because there are interesting things there that people, that should be seen. Okay, so we now go on to the next one, next page. Foundation studies in mechanics and so on. Let's breeze through it. I don't have much time. Okay, I told you about the Planck radiation law. I couldn't understand this. So what did I do? I've done 2 experiments in my life. One was in electrochemistry with electrodes, and the other one was me, a theoretician. I went to engineering to test this out because it seemed so strange. So I went there and I did all the tests. There was a conductivity apparatus mainly for student demonstration, but that's the only thing that engineering had. We didn't have anything in our part of the world. And so I did it, and I showed, in fact, that it is mainly 1 to 4. The linear power radiation heat transfer was 1 to 4. All right, this is the form of it. So that is also very interesting. I also did something strange. I noticed under a vacuum that if I had a foil put in a vacuum and measured the temperature in the center and the surface, there was a distinct 0.05 Kelvin separation temperature. Now, I developed a whole theory to explain that, and I also, putting aside all the conjectures, the radiancy based on these theories are actually different, and this might be of importance in astronomy. Now, I also developed, if there are temperature differentials, a development and a complete extension of the Kirchhoff law, and also of developing a thermodynamics with equilibrium temperature gradients. Now, that is an oxymoronic statement. An equilibrium system, if you're making use of momentum transfer, is not, will always have the same temperature. But this is what we developed rigorously. Okay, but to save you people of the international order, Robert Till provided a few years later something completely similar to what I was saying. So this inadvertently or otherwise adds credence to the Platonic ideology of the invariance of natural law and its independence from the mind and human discourse. That means if you follow the pyramid, since there's only one science, you can forget yourself and your needs and burn joss sticks, okay, to this. So there we are. So this is basically the entropy differential when this is the coupling constant. This is a top journal, I'm sure. Less important than the other. Okay, mechanics, quantum theory, I'll breeze through very quickly. Over here, I show that if you're using the same domain space, this is proven rigorously, making use of functional analysis, that you have full transitivity, and so the commutation relations, if you have transitive relations, you do not have Heisenberg uncertainty. I also checked the Heisenberg and the wave theory, and I found that the coordinates are such that the particle coordinates are the same. So if you are dealing with the same domain space, you do not have Heisenberg uncertainty. Lastly, also, the variation principle that was used, if this is a conservative Hamiltonian, you do this, you get 0. That's what Schrödinger did in order to derive his wave equation from the de Broglie theory. And so I did something similar to this and was able to derive all the EP, I could derive reciprocity relations in thermodynamics, making use of these types of potential and saying that this is equal to 0. This is a trivial variation, but I could reproduce linear irreversible thermodynamics using this method. Also, the Einstein-Podolsky paper, please read it, it's only 1 page long, constantly refers to the commutation relations in order to speak about the incompleteness, right? So if this doesn't hold, then EPR also can be questioned. Okay, molecular dynamics. The first thing was I did some work in Monte Carlo when I went for my first sabbatical. When I go to sabbaticals, I work and learn things. And I also wrote a note of this where I derive a set of equations for non-reversible. If you do Monte Carlo, the transition probabilities are Pij equals Pji. In this case, it isn't. And I also derived another form of transition probability where Pi is equal to just Pi, you know. You can check it out. So this is a new funny form. Interesting, but I have not worked on it. Okay, chemical reactions. I first went to Norway to learn NEMD. I had to go through every line of code. And then I applied it to a dimer system. I could explain the Hammett-Taft-Curtin relations and also delta G. And I showed that the standard free energy change is got nothing to do with what they tell you in textbooks, reactants and final state. Somehow, the height of the barrier actually determines the delta G, you know. So that is something very interesting and counterintuitive. Okay, then I had to derive in any MD, if I'm introducing a chemical reaction, you have many potential surfaces interacting, you know, because the free particle has got one potential, the chemical system has another. How do you match them together? So I had to devise an algorithm before I could proceed. Now, so this is what I did. Now, other thing is that when I started to study chemical reactions, I discovered that basically the way in which kineticists describe their rates does not bring in the activity coefficients directly. It's an incomplete description. And also, you have another set of coefficients called reactivity coefficients, okay? This is, you can see here. And lastly, I was reading a book, and they were describing a ballerina skating. And when she opens herself, it's slower. When she comes closer, the spin is greater. And I also went to Sunway Pyramid or whatever, and I saw all the young people skating. And so I thought, when I saw all that, it was wonderful. And I felt that this could apply to my molecules in the simulation box. They're spinning around and rotating. And so it seemed to me that you could actually describe the whole of, in a model system by making use, this is my potential over here. It's a hysteresis loop. It forms here and it breaks here. But the point here is that there we are. You have two species coming together and breaking. So when the bond extends, it's spinning. The moment of inertia is different. When it comes together, the moment of inertia. So it seems to me that it is the rotational value is very important. In quantum theory, you have all kinds of things, hindered rotations, blah, blah, blah. No, that I agree. But in a simple model, it seemed to me that it is the moment of inertia, and I believe that it's the microwave. That's the reason why microwaves, work here. So this is the theory. You have heat. Normal rotation is heat, but then if you try, when you tear it apart, there's also a work element. So just looking into that, you could derive the free energy and the work terms. And then you can derive a whole set of equations. And one thing I didn't have was a probability distribution. I didn't look into that, so I had to make some approximations, but you still get exceedingly good quantitative, semi-quantitative results, And the theorems, these are the theorems. It's a probability factor that I did not compute, but you can easily do it. It's just binning the results. Okay, so these are some of the things. Oh, another thing, the Curtin relations. The Taft-Curtin relations are given. Dr. Inyas will, it's a given, and there's no theoretical basis behind it. So this theory is able to account for it completely. as you know, completely. Okay, physical chemical properties of liquid mixtures. Now, in 2010, there was this need for postgraduates and mentoring or whatever. So from about 2010, and there was a postdoc from India who insisted to work with me. And again, kind person, I didn't want to throw away people. So what we did was I set up a non-specific liquid state lab for postgraduate research to be undertaken by researchers, students based on their personal interest and willingness to take risk. Since this work is not externally sponsored or encouraged, if you have built up a clientele relationship with Professor Robinson at Oxford, all this work will be guaranteed. But if people are asking their own questions in a vulnerable third world environment, they require courage of the highest order of courage. So I wish to apply my theoretical and computational studies to challenge and cultivate postgraduates' deductive capabilities of critical importance, and this in the small and medium scale industries. When they go for their, they will have to graduate from their training stint here is the stint here as students. We need people who can solve problems and think outside of the pyramid, all right? And so the thermodynamic properties of liquids are so complex that you can create any number of stories. And so this will be good for many of our students who are perhaps not so well prepared, all right, because of various circumstances. So this was the reason why I worked on liquids. And also, the data that you produce is of great use to industry. It was productive as well. Okay, so we employ all kinds of different methods, simple methods. You know, we can do it in our lab. These are the things. And so we have rationalized all these data, you know, in some recent writings. Now you notice, now there's a string of names in whatever I publish because there are others involved. So I propose to extend this basic laboratory to photoelectrical processes because fossil fuels are on the way out. And I hope that retirement would afford me the possibility of extended stays in all these centers that I would have to visit in order to understand and to be involved in the research. So this is good. Now, employment of academics and residents is difficult, you know, because you have to stay here and, you know, you don't have freedom of motion, which I think is exceedingly important for academics. And UM has appreciated this in terms of giving generous sabbaticals, and I think it should be extended in the future. Okay, these are some people in my recent venture, belated research venture. These are very courageous people. Yao, for example, developing his own theory of ultrasonics, and again, because of the pyramid, everything must appear at the center and not at the periphery. Poor chap. But he's very brilliant, and these are the, for example, in ultrasounds, I got an instrument from India, and we play around with it. For example, these are the spectrums, and these are some of the equations that he has. These are the way he rationalizes. It's interesting that in ultrasound, you cannot separate the machine from the electronics, you know. It's not separable. So very good results here, and brave people. Okay, and then other more conventional things are, for example, sigma profiles, being able to deduce it from the Cosmo-RS method. Okay, outline, concluding remarks, only 3 and I'll be done. Selfish aspects to my conclusion of the talk. These are the selfish parts. This is boring, the most boring. The work describes, covers a wide area. It appears that in the years ahead, a lot of effort must be spent in going deeper into the experimental and theoretical analysis. Computer simulations would be good, but you also need to write your own. No, nothing commercial will help, software or hardware. Oh, another thing about Yao. In one of his deductions, he talked about the separation of peaks, and it's up to 0.000 up to 6 decimal places. Our simple Indian device is only up to 3 decimal places. If you want to go further, you've got to make your own machines. this Malay academic needs to make our own machines. It's already here. We really need to build up our technical competence, if you want to ask scientific questions. This is very important. Okay, so this is the selfish aspects, right? So all that is all selfish. Now, less selfish aspects. It is possible to ask most basic questions in the physical sciences as a result of environmental and cultural motivation, and results can be far-reaching even in deprived environments. I did my electrochemical experiments because I had to teach undergraduate students in the not supposed to be in Malay, for the educational majors. So I started to think about things like the non-constancy of the chemical potential of the electrode, and that questions the whole Faraday concept, of charge distribution. Anyway, so there we are. So you see, the thing here is that if you indulge in this kind of thing, the KPIs, the chronology from start to finish is 30 years, and it just doesn't follow the administration, Only research that is open-ended and non-structured can help us address affordably the problems faced by society here that has to incorporate the human factor. Then we also need to develop a very high responsible media which has got a high volume but also very high standards, not at eliminating people, but on improving their work, not to cut them off, but to sharpen them, That is also very important. If you have 1.5 billion Indians in horrible conditions, they have lots of problems, and the scientific media must be there to ensure that everybody has a fair shot at addressing these issues. Number 3, non-selfish aspects. There are 3. I hope that the research experience of the last 3 decades in a non-conventional and personally costly manner can serve as a means of enriching those who wish to do independent research because of its pedagogical contribution through discussion, human relations, and exchange of ideas. So I'd like to talk to people who have the guts to want to ask their own questions, okay? I think I can serve that. With the prospects of retirement ahead, I hope to use some of my free time for such intentions at the regional level. Lastly, the essence of scientific research is the anamnesis or memory transfer of work and relationships and skills over the generations. When this does not exist in a research environment, then one is dealing with a dissipative structure with the drainage of intellectual, administrative, social, manpower, and infrastructural capital over time. I believe that much of the poverty in the third world is due to the absence of these cultural traits. It is absolutely essential to ensure that all of the above cultural features are present in our institutions if they are to serve a non-parasitic function in our society. So thank you for your support, presence, and participation. The end. That ends the talk. Thank you.
Congratulations, Prof. Dr. Jesudason, for their brilliant and inspiring lectures. And now it is my pleasure again to invite Professor Dr. Zanaria Abdullah for her concluding remarks.
Okay, thank you, Prof. Jesu, for such a very interesting lecture and a brilliant one. And being an organic chemist, and I need to summarize all this physical, theoretical chemistry. I'll try my best. Right. The talk just now highlighted fractions of some of the results and the outcomes of the impossible questions posed over 30 years in the field that you're working on. So I'll just highlight a few things. And firstly, in the field of thermodynamics with the application of inclusive of electrochemical system, whereby Prof. Jesu describes the development of in deriving minimum entropy production beyond the Gauguin, postulating the new entropy forms, etc., etc. And he also include the applications of potential theory and so on and so forth. And the second field that his contribution is in the statistical thermodynamics or statistical mechanics, where he listed as more than 10 contributions in this field, and ranging from a zero entropy trajectory with applications, as well as using a Brownian motion treatment of the black body cavity resonator. And then also it was found that it is possible to relate the Planck constant to the relaxation time of the electronic oscillation lining the cavity and the other related variables. And the third field that he brought us through is in the field of mechanics, quantum mechanics and radiations, whereby he described the extension of the Kirchhoff radiation law and proofs for the common domain space, and that the Hensberg uncertainty principles cannot be obtained from the Schrödinger wave functions. I think that's all that I'm going to summarize upon. There are other topics that he brought us through, for example, in the molecular dynamics, or MD, as well as NEMD simulation of complex systems, as well as the non-specific liquid state laboratory for postgraduate opportunities in independent research. And thank you, Prof. You brought us give us quite a lot of contribution there. And I'm not going to take much of the time. Finally, let us once again put our hands together to thank Prof. Jesudason for his exciting speech. Thank you very much, Prof. Okay.
Ladies and gentlemen, thank you very much, Professor Dr. Zanaria Abdullah, for chairing this lecture. So with that, ladies and gentlemen, we almost reached the end of this event. I would like to thank the management of Faculty of Science, the International Corporate Relations Office, Warga Universiti Malaya, and all of you here for taking your time to be with us to celebrate these memorable occasions. I would like to apologize for any weaknesses from our sides in organizing this lecture. Before we part, just to let you know, the refreshments will be served at the outsides of this hall. And with that, thank you and have a pleasant afternoon.